Dear colleagues, dear guests, dear students, and also our partners who have found the time to join us today. It is my great honor to introduce today's speaker to you, Professor Robert Tarjan. He is the James S. McDonnell Distinguished Professor of Computer Science at Princeton University, US. And also, many of you know, he is a preeminent figure in theoretical computer science because his work has influenced and shaped both theoretical and practical aspects of computer science. His work is widely recognized. He is cited more than 100,000 times. And also for his contribution, he was awarded Turing Award in 1986. Today, he will give a talk, My Life with Data Structures. So thank you very much for joining us, and the floor is yours.
Thank you. Thank you. It's a great pleasure to be here in your beautiful country and your beautiful city. This is the first time I have been to Estonia, and I'm really enjoying it. So I want to tell an origin story today, but let me first just mention how privileged I've been over my life. I want to acknowledge my wife, our 5 children, our 6 grandchildren, because they are the ones who give meaning beyond algorithms. And all of my amazing academic colleagues and students, brilliant people who made many of these ideas possible. The best thing about working in a field such as this one, I think, is the ability to collaborate with other wonderful scientists. So I want to tell you an origin story, and I've been around for a while. I was born in 1948. I grew up in Pomona, California, Southern California. I had an amazing math instructor in 8th and 9th grades who gave us piano's axioms. So I was doing proofs by induction in junior high school, and I just fell in love with mathematics. From there, I went on to Caltech, majored in mathematics. And I had an opportunity to do some very early programming. The first actual machine that I programmed on was something called the Bendix G15. It's amazing how much technology has changed over time. This was a refrigerator-sized machine, had 2,000 words of memory on a drum. Input was by paper tape. It was very primitive. The first real computer I got a chance to program on, I was able to program on Fortran instead of assembly language, which was a miracle because you could express your mathematical ideas and turn them into something that would actually run. So let me start with the first part of this. Okay. So I went to Caltech as an undergraduate majoring in mathematics. And when I was working in the summers, I got a chance to think about problems like the 4-color problem. So this is before the 4-color problem actually got solved. This led me into the question of planarity testing, which led to depth-first search. And this is the first part of the story that I want to tell. So the 4-color problem is very easy to state, like many combinatorial problems, easy to state but hard to resolve. Think of these faces as countries. We want to color the faces with a minimum number of colors so that no 2 countries sharing a common face have the same color. Now, this is a dodecahedron. There are 12 faces here. You will notice that inside we have a pentagon, and around the pentagon, we have 5 other faces. So the pentagon has to be 1 color. The faces around the boundary, we could use 2 colors, but if we go around the boundary with 2 colors, we end up at the end with, say this is red, blue, yellow, blue, yellow. Now this is adjacent to 3 different colors. We need a 4th color. For the dodecahedron, we need 4 colors, and in fact, you can color all the faces with 4 colors. And indeed, the conjecture was that you could color any planar graph with 4 colors. This was proved that you could use 5 colors. 5 colors sufficed, but for a long time, indeed until 1976, no one knew how to do it with 4 colors. But there were ideas, actually computer science ideas, that bear upon this problem. You could try to do a proof by induction, simplify the map, find some region that you could remove, color the rest of it, and then plug the region back in and color, no matter what the boundary was colored, color the inside, and prove that there was always a finite region that you could remove, color what was left, and then fill in the results. So this concept existed, and this is what ultimately led to the proof. I was, as a young high school student, just playing with these kinds of reducible configurations. I didn't have enough computer power or enough knowledge of the calculations that you had to do to be able to prove this. But this is, in fact, the way this theorem was proved in 1976 by Haken and Appel. A beautiful result from a computer science point of view. Many mathematicians have questioned it, viewed it as a giant case analysis that you need a computer to verify, is that legitimate mathematics or not? Well, I think it is, and of course these days with ChatGPT and such systems possibly doing some of our mathematics for us, there will be more and more computer-generated solutions to mathematical problems. In any case, they beat me to the punch on proving the 4-color theorem, but there's another question lurking in here, which is, this is a graph, it is embedded in the plane. That leads to a question, given a graph, when can it be embedded in the plane, and how can you do an embedding? So Korotowski, back in the 1930s, proved this beautiful result, which a mathematical theorem that says a graph can be embedded in the plane if and only if it does not contain one of these graphs. It's a generalized subgraph. So the K5 is a complete graph on 5 vertices, and the K33 is a complete graph on 2 sets. It's a complete bipartite graph on 2 sets of 3 vertices. Each of the 3 on the one side is connected to everything on the other side. This one, K33, there's a childhood puzzle. You have 3 houses, and you want to connect all 3 houses to a water plant, a gas plant, electricity plant, by pipes with no 2 pipes crossing. Can't be done unless you cheat by running one of the pipes underneath one of the houses. So I was at grad school at Stanford taking a class from John McCarthy in Lisp programming. He gave us several options for a programming project at the end of the semester. One was implement an algorithm, write a program in Lisp to tell whether a given graph is planar or not. Now, this is a nice mathematical characterization, but it doesn't lead in any obvious way to a very efficient algorithm. First of all, you would have to try all possible sets of 5 vertices to look for K5 and all possible sets of 6 vertices to look for K33. And furthermore, it's not just subgraphs you have to look for. You have to allow the possibility of intermediate vertices along all these edges. So I had various fellow students who tried to use this idea to come up with an algorithm that they could actually implement, and they all failed. But I discovered this interesting paper by Lempel, Evan, and Cedarbaum in 1967. So I was in grad school from 69 to 72. This would have been 69, 70. They gave an algorithm which uses a different approach to try to test for planarity. It embeds the graph in the plane, or tries to, by embedding one vertex at a time and keeping track of all possible embeddings. And every time a vertex is added, the number of possible embeddings is reduced, And they expressed the set of possible embeddings using a formula with essentially two kinds of connectives. You can think of them as and or, but they weren't exactly that. So I took this algorithm, I implemented it, I showed that it could run in n squared time, where n is the number of vertices, if it were implemented carefully, and I succeeded in actually getting a reasonable grade in this course, and I was the only one who came up with a running planarity testing algorithm. So I was interested in graph algorithms, planarity testing. Summer of 1970, John Hopcroft came from Cornell to Stanford on sabbatical, and we shared an office. He was a visiting faculty member, I was a grad student, and we started talking about graph problems, and we looked at depth-first search. So we were trying to consider properties of depth-first search and what we might be able to do with it. So here is a directed graph. What is a depth-first search? This is just a maze traversal process, if you will, and it goes back to Greek mythology, actually. We start out at some vertex, say vertex 1 here. We choose some edge to traverse, let's say the edge from 1 to 2, and then we keep going as far as we can before we have to back up. So I've numbered the vertices in the search order here. 1, 2, 3, 4. We go back to 3, but we've seen 3, we immediately back up. We can't go this way. This is a directed graph. We can only traverse the arcs in one direction. So then we back up to 3, back up to 1, back up to 2, back up to 1, and so on. I'll come back to this. What can we do with depth-first search? Well, we were able to characterize properties of depth-first search, and one thing I did was use it to find strongly connected components. So if we're looking at a directed graph, the strongly connected components are these sets of vertices that are mutually reachable. So this is the same graph that we had before. The dashed edges go between components, so 7 and 4 are in different components. The solid edges are within a component, so 3 and 4 are mutually connected, but we can't, if we leave 3 and 4, well, we can't leave 3 and 4. We can only get into 3 and 4. 1 and 9 are mutually connected, but if we leave 1 and 9, we can't get back in. 2, 5, 6, and 8 are mutually connected, and 7 is all by itself. So we have 4 strongly connected components, and these components can be ordered in a way so that every edge goes from a smaller component to a larger component. In this particular example, the ordering is unique because 1, 9 has to be the first component. It's the source component. Then we go to 5, 6, 8, 2. Then we go to 7, then we go to 3, 4. So first component is 1, 9, second, third, fourth. Turns out you can use depth-first search to compute the connected components, and this relies upon the fact that depth-first search decomposes the graph, in particular the edges of the graph, into 4 different kinds of edges. So let me just mention how this works. This is the same graph. If we start at 1, we go from 1 to 2. An edge that takes us to a new vertex, that's going to be a tree edge. Depth-first search and any other kind of search builds a tree rooted at the start vertex. It gives us a unique path to every vertex. So we go from 1 to 2, 2 to 3, 3 to 4. And now the edge from 4 to 3, that's a different kind because it takes us back to something we've seen before. And in particular, it takes us to a vertex that is on the current path. So depth-first search maintains a single path from the starting point, and it either extends the path or it backs up by a step. It's the unique kind of search that is completely local. So you think of Theseus and the Minotaur unrolling the thread, taking it forward or backing up to figure out how to get back to the entrance to the maze after he kills the Minotaur. In any case, this 4-3 edge, this is what is called a back edge or a cycle edge. It forms a cycle here. So this red edge guarantees that 3 and 4 are in the same connected component. Now, if we continue the search, we see some other red edges in here. The edge from 9 to 1, the blue edges form the underlying spanning tree. The red edges from 8 to 5, 8 to 2, 9 to 1, all form cycles in the graph. And then there are two other kinds of edges. There are edges like the green one, there's only one in this example, which is a forward edge, which leads us in the same direction as the tree edges, but is redundant in the sense that we can get from 1 to 2 to 3 along a tree path, or we can get directly there from 1 to 3. These edges are irrelevant for the strong components. And then we have edges between branches of the tree, the purple edges called cross edges. What cannot happen here, this would seem completely general, except what depth first search gives us is every purple edge, every cross edge goes from a larger to a smaller vertex. That is, we cannot have a purple edge, for example, from 4 to 7, because if we did have such an edge, we would have traversed it when we were at 4, and it would be a tree edge and not a cross edge. And this small limitation is enough to use depth first search to find the connected components if you use the right kind of data structure to keep track of what is going on here. And it turns out what you need is a stack to keep track of partially formed components, and then things get combined on the stack in a clever way. So it's possible to find the connected components with a single depth first search in linear time, and this is an important basic algorithm which gets used all over the place in practice. So that was kind of one nice, relatively simple application of depth first search, but we wanted to tackle a more complicated problem of planarity testing. How can we do planarity testing possibly in linear time? The answer is, well, we could try the Lempel-Evan and Cedarbaum algorithm, adding a vertex at a time, and I'll come back to that. But we took a look at an alternative algorithm which was invented by Auslander and Parter and actually fixed by Goldstein, which embeds a path at a time. This is maybe a more natural algorithm. So the observation is, what is the plane? The plane is characterized essentially by the Jordan curve theorem. If you have any simple closed curve, it divides the plane into two connected regions, the inside and the outside. If I embedded some piece of my graph, which is a cycle, and I now want to put another path in whose ends are on the cycle, but just the ends, there are two places I can put it, either inside the cycle or outside the cycle. So here's a path which could be embedded as the red path here, or on the outside as the blue path here, but it can't cross the black path because that part chops the plane into two pieces. So one path has to go on the inside or the outside. Now what if we have many paths of this kind that have attachments to the cycle at just two places? Well, certain kinds of paths have to be on opposite sides. Here, the red path has to be on the opposite side than the blue path because the endpoints overlap. But the two red paths, I've drawn them as both being on the inside, but we could equally well move either one of these. We can move this one to the outside if we want to. Or we could take the red and the blue paths and switch the places of both of them, put the one on the inside and the other one on the outside. So this leads to the idea of an algorithm which is partition the graph into an initial cycle and a collection of paths such that each path has in common with the stuff that you've already embedded, just the endpoints, and figure out the possible placements of each new path in turn. And when you add a path which implies some kind of extra constraint, You maintain a data structure that keeps track of all the possible embeddings. Now, in general, there can be an exponential number of embeddings, so this is not entirely obvious. This is an illustration of a general phenomenon. Strong components was the first one. We turned it into a data structure problem where you use a stack. Here we had to use something more complicated, which is a hierarchical stack. It's actually a collection of, it's a stack of stacks, and each stack is divided up into two sets corresponding to paths embedded on the outside and on the inside. And when one gets a overlap, these pairs of stacks no longer can flip independently, but they get glued together, so everything gets cemented together, and keeping track of that led us to a linear time algorithm for planarity testing. All right, so the bottom line is decompose the path into edge disjoint paths, and the way to do it is to run a depth first search and add paths one at a time to the planar embedding, keep track of all the possible embeddings in the data structure, which is this rather idiosyncratic idea of hierarchical stack. And then every time you add a new path, update the data structure to keep track of the remaining set of possible embeddings. And we were able to do all this in linear time in the graph size, which is best possible to within a constant factor. I should say here that back when we were doing this, there was a question actually of how to measure the efficiency of computer programs. So Don Knuth, who was at Stanford, started writing his famous book series, and he was counting assembly language or machine language instructions. He was doing fine counting of algorithms. And we thought, this is too fine-grained. First of all, it's too hard to do. And second of all, it doesn't reflect the possibility of different kinds of machines with different speeds and so on. So he made the choice to ignore constant factors. And this led to the idea of big O notation. And I think this way of measuring the performance of algorithms was very important, because it gave something that one could actually do. You could analyze algorithms, and you didn't have to get down into the weeds, and it was machine independent, and it was reasonably realistic. I mean, if an algorithm has a good running time, in the worst case, especially linear time algorithm, the constant factors tend to be small. So I actually, this was my PhD thesis, I programmed this algorithm in Algol W, which was the Niklaus Wirth's version of Algol, which we used at Stanford at the time. It was a whole box of IBM punch cards. Back in those days, you put your program on punch cards, take it to the computer center, it runs overnight, you get a printout back with 100 error messages, and then you start over again. It was very primitive. Nevertheless, the algorithm got implemented, it ran, I got my PhD, I went off to Cornell, all was happy. Now, coming back to the other algorithm, the Lempel-Evan and Cedarbaum algorithm, turns out there's also a way to implement this one in linear time. This is the vertex addition idea instead of path addition. So in some sense, at one level it's simpler, but at another level it's more complicated. Vertex addition, you have to add the vertices in a particular order, and again, depth first search is the key to discovering that order. That is a so-called ST order. So one component was to find an ST order, an order of vertices to be added to run the LAC algorithm. That I did together with Shimon Evan. The other thing that was needed was a way to implement their symbol manipulation business, which actually did the planarity testing. So this was done independently by Kelly Booth, who was a PhD student at Berkeley, and George Luker, who was a PhD student, I think in North Carolina or someplace like that. And they discovered they had the same results, so they ended up publishing together, and they both got their PhD thesis, which was good. But they were not aware of this application, but after I pointed it out to them, they put it in their paper. So both of these algorithms run in linear time with reasonably small constant factors, and they're rather disjoint in how they approach the problem. So this is an example of exploring the design space. There was no systematic exploration of the design space, but it turns out there are two rather different, more or less equally efficient solutions to the problem. So big O notation, ignoring constant factors is good. Exploring the design space is good. Lots of problems, graph problems, other sorts of problems turn into data structure problems where you need to do some sequence of simple operations, many of them, keep track of exactly the right information over time. All right, now after I got my PhD, I followed John Hopcroft back to Cornell. That was my first job. I had a fire engine red Mustang. I grew up in Southern California. I left Palo Alto in the middle of winter, drove across the country in my rear-wheel drive car. I get to Ithaca, New York. There's white stuff falling out of the sky. I'm sliding all over the place. I was challenged by the weather, shall we say. In any case, I got interested in another data structure problem, the disjoint set union problem, and ultimately, over the course of 3 years, ended up solving it, and that's the next part of the story here. I lasted 2 winters at Ithaca at Cornell. May of 1973, as I was leaving town, it was again snowing, beautiful puffy snow, spring snow. I took that as a sign somehow. Ithaca is a beautiful place, but the weather was not for me, at least in those days. But now we have global warming, so things have changed a bit. I talked about strong components in directed graphs. Here's an even simpler problem, maintaining connected components in an undirected graph, kind of the most basic problem in an undirected graph. So a connected component is a set of vertices such that we can get from one and back to the other one. But now we can, since the graph is undirected, we can go in either direction. So like strongly connected components, but simpler. How many strongly connected components? This is not a rhetorical question. Anyone?
Three.
Thank you. How many strongly connected components? 3, thank you. How many strongly connected components? By induction, there must be 3. I'll let you figure this out later. What if the graph is really big? All right. So one approach to finding connected components is to run graph search, start from any vertex, see where you can get. The set of vertices you can get gives you one component. Start out with another vertex that hasn't been reached yet, generate the connected component that it contains, and so on. That's a natural linear time algorithm for finding connected components. But now let me change the problem. The graph is not static. I'm adding edges one at a time. I want to maintain the connected components as I add edges. So I want to be able to do queries given 2 vertices, are they in the same component or not, and add an edge to the graph and update whatever the data structure is that's keeping track of the components. So here's an abstraction of that problem that has many applications. What is really going on here? We have a partition of the vertices into connected components. We can think of it, initially there are no edges, so every vertex is in its own component. We start combining the sets of vertices into bigger and bigger components. What is going on? Well, two things. First of all, we want to be able to identify when two vertices are in the same component. So let's assign a specific vertex in each component to be the leader of the component. We'll have one operation that just returns the leader, given any vertex, returns the leader of the set containing it. So if I have a find operation, I can then tell whether two vertices are in the same component by doing a find on each one and testing for equality. Now I need to be able to put components together, so I'll do that by a unite operation, which, if two vertices are in different sets, combines the two sets into one, and if they're in the same set, does nothing. Now I'm going to let the algorithm choose the leader of each new set, because as a user, I don't care too much which vertex is the leader. And I will point out that if I have a way to identify the leader of a set and I want to keep track of additional information about the set, such as its size or some other properties, I can store that information with the leader. So these are the two operations. I want a data structure to do the two operations efficiently. This is the disjoint set union, or sometimes called union find problem. It can be used to solve the connected components problem, and it has many other applications, some of them obvious, some of them not so obvious. There's a beautiful, simple data structure to solve this problem that I'll call the compressed tree data structure. It's sort of the most primitive way to use trees as a data structure in algorithms. So we'll represent each set by a rooted tree whose nodes are the elements of the set. The root of the tree is the leader of the set, and every node has a pointer to its parent in its tree. So if my hand is a tree, the pointers are going up along my fingers, and this part is the root, and we'll just put a self-pointer to the root. So that's the representation. Every set has one tree representing it. So to do a find, I just follow parent pointers until I get to a node pointing at itself. That's the root. I return that node. To do a unite, I do two finds on the two nodes. Say I'm trying to unite V and W. I find V, it's the leader of its set is X. I find W, the leader of its set is Y. If they're equal, V and W are in the same set, I don't do anything. If they're in different sets, I've got the two roots, I can make one of them point to the other one. And I can do it in either direction. So that's how I do the unite. So everything is based upon these find operations. Walk up a path, find a root. Walk up a path, find a root. Put in a new pointer from one root to another root. Now I want to do a long sequence, an arbitrary long sequence of these operations, intermixed finds and unites. And the question is, how efficient is this? Well, as it stands, it's pretty terrible because it's easy to build a tree that's just a long path. And then if we repeatedly do finds on nodes near the bottom, it's going to take us linear time per find, but we would like something much closer to constant time per operation. So there are at least two improvements that one can try. One of them is to exploit the fact that when we're doing the linking, we can make either root point to the other one. So we'll make that choice intelligently. And the second one is we don't care what the structure, the internal structure of a tree is. It can be anything. So when we do a find, we'll change the structure to make the tree shallower. So how is that going to work? Linking by rank. The original heuristic was linking by size, in which we make the root of the smaller sized tree point to the root of the larger sized tree. We can keep track of the size in the root, in the set leader. So this is a constant time operation. Turns out so that indirectly is a good idea. Putting the smaller tree, attaching the smaller tree to the larger tree reduces the worst case time per find from linear to logarithmic. So we get an exponential improvement. But here's a more direct way to do the same idea. We called it linking by rank. Instead of linking by size, we're essentially linking by maximum path length. So we'll assign, each vertex is going to have a rank, initially 0. We always attach the smaller rank root to the larger rank root. When there's ever a tie, we increase the rank of 1, and we attach the smaller rank 1 to the larger rank 1. It turns out, so if you ignore path compression, which I'm about to get to, that's linking the shallower tree, the one with shorter maximum path length, to the deeper tree. And again, all by itself, that reduces the worst case time per find from linear to logarithmic. So we get an exponential improvement, and we've got a reasonable data structure. But now we can do something else, and that's the brilliant idea of path compression, which seems to have been independently discovered by Tritter, who was an IBM engineer, and Doug McElroy, who was at Bell Labs. And neither one published this, but it was published by later people. And the idea is, a picture will illustrate this. I do a find on a node, say 1. I walk up the route, up the path to 10, which is the root. I want to return 10. I know that the answer, not only for 1, but for everything on the path is 10. So why not change all these pointers to point to 10? That's path compression. Walk up the path to find the root. Walk up the path a second time to change all the pointers to point to the root. So that's the result. Now if I do another find on 1, or indeed on 2, 5, or 8, it's constant time as opposed to whatever the path length was previously. And the only way to increase the time of a find for any of these nodes that were previously found is to link 10 to something else. So the links are going to make paths longer, and the finds are going to make paths shorter. And now we have this interesting dynamic situation where there's a tension between the finds and the links. And the question is, how efficient is this data structure? In particular, what is the total time to do a sequence of, let's say, m operations on sets containing a total of n elements? So we start out with n singletons. In our connected component application, that was the vertices. And we do m operations. You can think of m finds or m finds intermixed with unites. Each unite does 2 finds. Doesn't matter because we're ignoring constant factors. In particular, the hope would be that the total time is linear in the total number of operations, even though you can have individual expensive operations. Now with linking by rank, we can only build paths of length log n, but we can still get an individual find that takes log n time. But maybe this compression process really improves things. So this was stated as an open problem in the early 70s. I think Knuth stated as an early open problem, and people kind of suspected that the answer was constant time per find, in fact. So let me illustrate the history of analyzing this very simple but surprisingly complicated algorithm. Some famous people who I won't embarrass came up with a constant amortized time proof, but it was incorrect. Mike Fisher gave a bound per find, which was double log of n. So you save another log factor if you combine path compression with linking by rank. And then Hopcroft and Ullman shortly thereafter gave a bound of log star n. This is the iterated logarithm, which is the number of times you have to apply the log to n to get down to 1. So very slowly growing, but only upper bound. So I was intrigued by these results, and I started working on the problem, and I asked the question, what if it's not constant time per fine? So I managed to construct a counterexample. So how do you construct a counterexample? If it's not constant time per find, that means that for any possible find length, say k, you have to build an example such that you can do lots and lots of finds, a linear number of finds, each of which the length of the path is k. And if you start playing with examples, you can build a recurrence to show that for any k, you can actually construct the thing. And what you get out of the recurrence is something called Ackermann's function, which I'll define on the next slide. And the alpha function is the inverse of Ackermann's function. This is a function that is non-constant, but incredibly slowly growing. You could never detect it by experiment. So I was making this transition from from Cornell to Berkeley, recall the car in the snow. I had this lower bound result, and then the obvious question is, well, is this a tight bound or is log star n the right answer? But Ackermann's function is so beautiful, it had to be the answer. So I spent my 2 years at Berkeley essentially working out how to prove that this bound was tight, that it is in fact inverse Ackermann function. This is inherent not only in this algorithm, but also it was later shown in any possible algorithm to solve this problem. Later there was a incorrect lower bound proof, and in 2005, Ryman Seidel, who was actually my academic grandchild, that is, he was a PhD student of one of my PhD students, and Mika Sharir, came up with a somewhat different upper bound proof of the same result. So what is Ackermann's function? This was invented by Ackermann to show, back in the days when this was in the 1930s, 1920s, 1930s, we in computer science know the Turing machine as the abstraction that captures all possible algorithms. But there was no formal notion of an algorithm until the Turing machine and several other equivalent notions were invented. And one of them was invented by logicians, mathematicians, logicians. It's the notion of general recursion, so recursive functions, if you will. And Ackermann's function was constructed by Ackermann to show that you need more than one variable. You need general recursion. Primitive recursion does not suffice. Ackermann's function is essentially a diagonalization over all possible one variable recursions. You can think of it as a generalized exponential, although it's a little bit disguised here. So this is a definition due to Pater and Robinson. It's got two variables here. I put one in the subscript and one in the parens. You can think of it as a family of functions, A0, A1, A2, and so on. The first one is n plus 1. That's one boundary condition. So A0 of n is n plus 1. AK of 0 is AK minus 1 of 1. That's for k greater than 0. And the killer, the main part of the recurrence here, is AK of n. AK of n is AK n minus 1 applied to AK of n minus 1. So you notice here that at least one of the two variables is decreasing, which means this thing is well defined, but it grows incredibly fast. If you unroll the main recurrence here, AK minus 1, AK of n is AK minus 1 applied to itself n plus 1 times, and then applied to 1. So roughly speaking, what happens is A of 0 is n plus 1, A of 1 is n plus 2, A of 2 is 2n plus 3, growing faster than 2n, A of 3 grows faster than 2 to the n, 2n to the n. A of 4 grows faster than a stack of n2s, and A5 is enormous. These things grow, in terms of k in particular, this thing grows incredibly fast. And alpha is essentially the inverse function. We don't have to worry too much about the definition. So here's this amazing function invented for a completely different purpose that comes up in the analysis of an algorithm. And what are we analyzing here? We're counting not the individual cost per operation, but the cost over a long sequence of operations. We'll get back to that point. So we've got some examples here where we've got data structures where we're doing repeated operations, and we're interested in the total time, and we don't care so much about the time per each individual operation. Lurking in here is the important notion of amortization, but we're not quite there yet. All right, so I went from Berkeley to Stanford, back to Stanford where I got my PhD. I was an assistant professor at Stanford. And I got interested in the maximum flow problem. We all know what that problem is. I'm going to turn it into a data structure problem here, something called a link cut tree or a dynamic tree. And this led eventually to the notion of amortization, to self-adjusting data structures, and then to splay trees. This is work that I did with Danny Slater, who was a PhD student of mine at Stanford, and followed me to Bell Labs, where we worked on splay trees together, and then went to Carnegie Mellon, where he's still a professor. So the maximum flow problem, we're given a graph with two distinguished vertices, S and T. We want to find a maximum flow from S to T. We've got a capacity on every edge. The capacity bounds the amount of flow we can send through the edge. So for example, these edges coming out of S have a capacity of 2. That's the first number there. What is a flow? A flow is an assignment to each edge between 0 and the capacity, with the property that at each vertex other than S and T, the total incoming flow equals the total outgoing flow. So if we look at that vertex, for example, it's got 3 units of flow coming in, one coming from here, and this edge has flow equal to its capacity, and this edge has flow 1, which is not its capacity, but we got 3 units coming in, and all 3 go out here. So this is actually a legitimate flow, and in fact, it's a maximum flow, which is the goal, which we can see because we've used up all the capacity out of the source and all the capacity into the sink. And many of you will be familiar with Ford-Fulkerson algorithm and the max flow min cut theorem, which justifies the algorithm. And let me illustrate it on a smaller example. The algorithm it's an iterative improvement algorithm. Find an augmenting path, which is just a path from the source to the sink along which we can increase the flow. Repeatedly find an augmenting path, send as much flow through it as possible, and repeat until done. One critical thing about this algorithm is that you need to be able to do rerouting. That is, you may send flow along the wrong path, and then you have to allow backing up. So to keep track of the backing up for each, I'll illustrate this in a minute, but for each arc, if we have a certain amount of flow going in the forward direction, we can send an additional amount, which is the capacity minus the current flow, but we can also send the current flow in the forward direction backward, which gives us residual capacity in the backward direction. So we have to consider both the backward rerouting and the forward routing. So let's look at an almost trivial example. This graph has a maximum flow of 200, obviously. We send 200 units along the top path through A and 200 units along the bottom path through B, and 0 is the initial flow. But suppose we pick the wrong path here. There's this funny edge in the middle. We can say, if we pick the SABT as our augmenting path, and the bottleneck is the AB edge, we can only send 1 unit along this path. And now if we choose the SAAT path, well, we can send 99 more from S to A and all of the 99 to T, which would be a good thing to do. Or we could send 99 to B and the same 99 to T, which would be a good thing to do. But if instead we choose the augmenting path that goes S to B to A to T, making use of the fact that we can send this 1 unit back from B to A, then we get this, and we're up to 2 units of flow. And after 198 more augmentations of the same kind, we get a maximum flow. Is this a polynomial time algorithm? This was what Ford and Fulkerson said. If you have integer capacities, you're always increasing the flow by at least 1 unit. Therefore, it converges. Therefore, we're happy. But as a computer scientist of the later generation, one is not happy with this solution. So the question is there a way to find augmenting paths that gives a bound on the number of augmentations that ideally would be independent of the numbers, so we don't have this hideous example? And in fact, there is, and it was independently discovered by Edmonds and Karp and by Dinitz, who was in the Soviet Union at the time. The Soviets were doing beautiful work in network optimization. There are several of them. We were not communicating with the Soviets. Use breadth first search to find an augmenting path. Always augment along a path that has fewest arcs. Then the number of augmentations is polynomial independent of the number sizes, assuming you can do arithmetic on the numbers in constant time. In particular, the number of augmentations is at most number of arcs times number of vertices, mn. That's all that Edmonds and Karp said. So if you look for each augmenting path individually, there's an extra m factor proportional to the number of edges, so you end up with a bound which is m squared n, which for dense graphs where m, the number of edges, is proportional to n squared, that's n to the 5th. Dinitz came up with a beautiful, also a data structure idea, which mass processed the augmenting paths of a given number of hops, reduced the cost per augmentation from m to n, ended up with a bound of n squared m. But that's preliminary to what I want to say, which is these augmenting paths, as we send flow, so I send flow along a path, some edge gets saturated, it gets removed. I still have these residual paths along which I've sent flow, and the classic algorithms don't keep track of what I've already done. Is there a way to keep track of what I've already done? Now, it's not as simple as just paths, because if now I find another path from the start vertex and it hits this other path and I break something, I'm going to end up with some kind of tree here. So it turns out what happens, the underlying process is some kind of manipulation of rooted trees. Now, we've seen rooted trees already. This is another version of rooted trees, but it's more complicated. We want to reuse the previous computation. So this leads us into a data structure problem. And what is it? Well, we've got a collection of rooted trees which change over time as flow is sent along augmenting paths. It seems that the expensive part is marching along a path to send flow all the way along. If we could somehow represent that entire path implicitly, we could send the flow all at once and maybe save time. So that is the idea. And what is the underlying data structure problem? I'll call it the link cut tree or dynamic tree problem. We want to maintain a collection of vertex disjoint rooted trees, and each one has a non-negative flow or capacity or something. And the trees are changing by linking operations, which makes the root of one tree a child of a node in the other tree. If you will forgive my abstraction here. Here we've got the source, here we've got the sink. The picture in the middle of this process is we've got these trees, and there may be some tree with the source in it like this. We need to find an augmenting path, so we find some edge that leads from the root of this source tree into some other tree that hooks these trees together. Maybe we connect here and then we connect here, and now we've got a path through here. We send flow along this path, and what is that going to do? That's going to cut at least one edge in here. So the underlying process is linking trees by adding edges and cutting trees by cutting edges. So those are the link and cut operations. We need to be able to find the root of a tree containing a given vertex. We've seen that before, but now in a more complicated context. We need to find the minimum arc on the path, the minimum flow value arc on the path, because that's the bottleneck. We got to be able to send the correct amount of flow on the path and then cut whatever edge has its residual capacity reduced to zero. So we get a somewhat complicated repertoire of operations, but here's a data structure problem. If we can implement these operations efficiently, we can speed up the Edmonds-Karp-Dinitz algorithm. And at this level, there's a solution for paths. We represent a path as a binary search tree. And then we're linking and cutting binary search trees. We get two logs if we use that as a solution. That was essentially discovered by Galil and Nahmad, also in the context of the maximum flow problem. But maybe we don't need one of these logarithms. So what is the picture here? This is the actual tree that we're trying to represent. We're going to break it up into a collection of vertex disjoint paths. In this case, the red paths. NJE, TQPLID, FBA, KO. And each of these, some of these vertices are in single node paths. The black stuff, the stuff outside the long paths, will just represent explicitly. But these long paths, we're going to represent each one by a binary tree. The most interesting one is TQPLID, which is represented by this thing, which is a binary tree where the order of the nodes is the order along the path, in this case from top to bottom, or from bottom to top, depending upon how you want to choose to do things. So this is the bottom node, Q is the next node, P is the next node, L is the next node, I, D, A, not H, just this set. Okay, so two things are now going on. We have to be able to do operations within these trees, and we have to restructure the path partition. The restructuring part, Galil and Nahmad showed, is log n time, and you can actually do it worst case, but it's not so simple. And if you use a standard binary search tree for each one of these, you get a log squared factor, and the question is, can you reduce to a single log time? So the first thing we did was try to do the standard worst case analysis, and we managed to get rid of the extra log factor using something called a biased binary search tree. Solves the problem, but not in the nicest way. But This doesn't have to be worst case. We only care about the long term. So maybe we can devise a data structure where in the long term it's efficient, but on individual operations it could be expensive. So in particular, we got this binary search tree in here. We need a binary search tree that's balanced most of the time, but not always. So this led us to the question of designing a self-adjusting binary search tree, and we're getting to the punchline here. So the notion that we were playing with for 15 years or something is that of amortization. It's this idea of looking at a long sequence of operations and adding up the total time for the operations, allowing individual operations to be expensive if cheap operations occur often enough. So if we have this notion, we can design data structures that are efficient in the amortized sense, not in the worst case sense. And maybe we get simpler, more adaptive data structures. So that led us to the idea of a particular kind of self-adjusting binary search tree. Let me just mention, where did we get this word? Well, amortized, you take out a big loan on your house, you pay it off in equal installments. It comes from Latin, to reduce to the point of death. What do we mean by it in the analysis of algorithms? We want to pay for the total cost of a sequence of operations by charging each operation an equal or appropriate amount. And the trick in these situations is first to come up with the right data structure, and second, the hard part, figure out how to do the charging argument. You need to keep track of what parts of the data structure are bad and what parts are good, and somehow charge the bad parts. And if one of these works, when you have an expensive operation, the bad stuff becomes good. That's exactly what was happening in the disjoint set union algorithm. You have long paths, path compression makes them short. Turns a bad situation into a good situation. Quantifying that is the hard part. So we played around with this idea for getting a self-adjusting binary search tree. Here's a binary search tree. It's just a way to store a set of items in sequential order so you can do searches fast. So I've stored letters here. If I want to search for E, for example, these are in sorted order left to right in the tree, so-called symmetric order. To search for F, I branch, to search for E from F, I branch left from F because E is smaller, branch right from D because E is larger. It's easy to build a good binary tree if your data is provided ahead of time. You can get log-in search, but the question is, what if you're doing insertions and deletions? So the straightforward way to do insertions is called leaf insertion. You follow the search path and insert the new item where the search falls off the bottom of the tree. So if I want to insert R in this tree, I search for it. It's bigger than F, bigger than M, less than X, bigger than P, fall off the tree, put R there. Now what happens if I start with an empty tree and I start doing insertions? I usually don't get the perfect tree, and indeed, if I insert items in sorted order, I get the worst possible tree, which is something like this, where the worst case access cost is linear, but I know I could do log n if I built the right kind of tree. So I'm trying to overcome this obstacle. In order to do so, I have to update the tree every time I do a insertion. I need a method to do updating locally somehow, to pull things up and push things down. And I also need some kind of definition of balance, which is going to guarantee maximum path length logarithmic. And it's got to be more flexible than just the thing is a perfect balanced tree. So this problem was solved originally by two Russians, Adelson, Velsky, and Landis in 1961 with the so-called AVL trees, which you are probably familiar with. There are many, many kinds of balanced tree schemes, red-black trees notably, actually invented by Bayer in 1972, but popularized by Gibas and Sedgwick in a paper in 1978. These are worst-case efficient data structures. Can we do something similar without keeping track of balance information? So here's an AVL tree. The balance condition is that from any node, the maximum path length down the left branch, the left side, is within 1 of the maximum path length down the right side. So you store a three possibility state in each node. Either the right side is heavy, or the left side is heavy, or equality. Red-black trees, every node is red or black. Every red node has a black parent, and the number of black nodes on every path is the same from top to bottom in the tree structure. The standard restructuring primitive is called a rotation. It operates like this. If I have a child of another node, a left child of node Y, I can push X up in place of Y and push Y down the other side. This takes constant time, restructures the tree, moves the A part up, pushes the C part down. The B part stays at the same level. I can transform any tree with the same order of items into any other tree on the same set of items with an appropriate sequence of rotations. And the way these balanced tree schemes work is that they do rebalancing along the access path every time they do an insertion or a deletion. I haven't talked about deletion. Complicated. There are many cases to handle the rebalancing. And also, these data structures are designed to minimize the worst case access time. They don't necessarily adapt situations where the access pattern is non-uniform. So the question is, can we do something similar without any balancing? Some kind of simple self-adjusting scheme. So that's what we attempted to do. The first obvious thing to try is something like path compression, like when you access an item, move it to the root by rotating it to the top, with the hope that when it's next accessed, it'll be cheap to access because it's at or near the top. But this breaks, and it's easy to construct examples. So we failed on that, but second try, do the rotations 2 at a time in the right order. This led us to this idea of splay trees. So splay means to spread out. And the way the operation works is when you do a access, any kind of operation on an item, it gets pushed to the root. It's moved to the root by rotations, but they're done 2 at a time. And here are the rules for rotations. In the interest of time, I won't go through the details. Here's an artist's perception of a self-adjusting splay tree. This was done by George Stolfi, who was at DEC Circ in the heyday of DEC Circ. He was a brilliant computer scientist, but he was also a great cartoonist. And many of the DEC Circ technical reports have cartoons that illustrate the concepts in the paper. So he did this for me when I got the Turing Award. So we were able to prove that this data structure, in fact, among other things, performs as efficiently as your favorite balanced binary search tree in this amortized sense. So log time per operation. But it has stronger properties. If you access certain items much more frequently than other items, they rise to the top, and you can prove that the behavior is, to within a constant factor, as good as if you built an optimum binary search tree, you knowing the access frequencies ahead of time. And we proved some other interesting properties of this data structure. And we were led to this audacious conjecture, which is essentially that Within the family of binary search tree algorithms, the Splay tree is as good as any, even one that knows the entire future ahead of time. So the situation is, I give you an initial tree, I give you a sequence of operations to perform, let's just say accesses. So you got to do a sequence of accesses. The cost to access an item is the number of nodes on the access path. You can also do rotations anytime you want, constant per rotation. I tell you the entire sequence, you design the optimum algorithm, I run the Splay algorithm. The conjecture is that the Splay algorithm, no matter what the access sequence, is going to perform as well as the optimum offline algorithm to within a constant factor. This is to say, so the term people use for this now is competitive. We say that the conjecture is that Splay is competitive, constant competitive with the best possible offline binary search tree algorithm. This problem is still open. This is my favorite problem in data structures. And there are good reasons to think the conjecture is true. There was very little work on this problem after the mid-1980s when we worked on it until Bob Wilbur at Carnegie Mellon, who was a student of Denny's after he moved to Carnegie Mellon, proved some lower bounds. There's a question of how do you get bad sequences here? It's not at all clear. So he came up with some lower bounds, and it was possible to build an algorithm on top of one of these lower bounds that was not constant competitive, but double log competitive, but it's not the Splay algorithm. And there has been quite a lot of recent work on questions related to this one. So even though many of these results now go back decades, we still don't understand these simple, repeated processes that come up in data structures. So for all of you young folks, here's a challenge. Prove or disprove this dynamic optimality conjecture, or invent your own data structure for which such a conjecture is true. And let me close here just making a few comments. My personal approach to research, especially these days, is the goal is to systematically explore the design space for fundamental problems and to come up with the best possible algorithms. Paul Erdős, who was a famous mathematician, had this notion of proofs from the book. That's the book up there. So we want to find algorithms from the book, algorithms that are as simple as possible, provable resource bounds for important input classes, and efficient in practice. The design space only expands as computers get faster and computer memories grow in size. I don't know if Einstein actually said something like this, but this quote, among many others, is attributed to him. You know, when you get famous enough, people attribute things to you. For example, I'm giving another talk and somebody generated a bio for me using ChatGPT, gave me 2 awards, important awards, that I haven't actually received. So trust but verify when you use these generative AI models. Make everything as simple as possible, but not simpler. Thank you very much.
Thank you very much for this inspiring talk. I believe few of you already have some questions in your pockets, so I think we can take a few of those also. Please raise your hand if you have one, and wait for the microphone, because then we can have it on the tape also. I'll give you more.
Thank you. We often have the impression that university also has to serve industry in some way or the other. Have you ever been contacted by the industry that here is a challenge, we are really struggling, we can't get it solve, I don't know, answer the query in sufficient time? Can you help us out?
The answer is I've had kind of a second career in industry. So when I was at Stanford, I started consulting at Bell Labs in New Jersey, and I was working with the research group, the mathematics research group, but I went there on sabbatical and stayed for 5 years. So there we were in a research group, but the charge to management was to bring the researchers problems that actually needed, problems from development and so on that actually needed solutions. So that's the context mostly in which I've addressed industrial research problems. I was doing the same thing later on at HP. We worked on various, actually a parametric maximum flow problem that had an application in SKU management for their product sales stuff. And I also worked on something that was scheduling for Disney was making movies using HP technology, and they had various high-performance scheduling issues. So I worked on some problems in that context. That's mostly, when I was in industry, I was working on problems with applications. Yes.
So I saw another hand right there. Dima, please.
Yeah, I just wanted to say a big thank you, Robert, for the lecture, but also a big thank you for all the contribution that you have had in the field. As somebody who was first studying your algorithms and then later teaching these algorithms, it's a big pleasure seeing you in person. I had a question related to something that is unavoidable, I think, these days is ChatGPT, obviously, and similar large language models. So you did mention this a couple of times in your talk that you have already interacted and there were some good results, obviously some interesting things that it has hallucinated. But how would you generally describe your own current progress or research in the era of the large language models? How did it change your perspective on things?
It hasn't changed the way I function, but I am curious to see whether these systems can be used to help solve some of these data structure design and analysis problems. There was a group from Google DeepMind who just visited the Institute for Advanced Study, which was in Princeton a couple of weeks ago, and I went to a couple of presentations by them, and they're trying to do mathematics using some combination of large language models and tying it to LEAP, which is a proof verification system. And they ran this on problems from the Mathematics Olympiad, which are very challenging problems, yes. So they completely failed on the geometry problems, but there was another group that was working specifically on geometry problems that was able to do those perfectly. They did quite well on the algebra and analysis problems, and they completely failed on the combinatorics problems. So anecdotally, the combinatorics problems seem to be a challenge for these systems. I mean, they are great at synthesizing existing information, but they can't make the creative leaps yet. Maybe they will. I think there's a possibility for great tools. I worry that people are going to use them to replace human beings, whereas they should be used as tools to enhance human beings. So I would like to see them used as enhancements to all of our activities.
Yeah, Robert, also from me a big thank you for coming to Tartu and again to Riga. And my question, can you describe the moment you found out that you were receiving the Turing Award, and how did you find out?
I don't remember. I got a telephone or a phone call. I was on vacation. It was summertime. I was in Massachusetts. We were staying at the beach, actually. It was a wonderful event. Although I have to say, the Turing Award was a much smaller thing back in the day when I got it. I did a lot of this work when I was pretty young, and I was very fortunate to get this award back when it was much less competitive than now. But I get to ride on the glory of the people who are getting it now, which is kind of a fun thing. So now it's worth $1 million. Hopcroft and I got, I think, $1,000 to split between the two of us. So. And a silver bowl from Tiffany's.
So you didn't think it was a fake call? You didn't think it was a fake phone call when you got the call?
It was exciting. It was exciting, but it wasn't about the money. It was about the recognition. The awards are strange because there are many more deserving people than will ever be able to get an award because there aren't enough of them. So I am kind of two minds of it. I'm happy for the recognition, and of course, what has been my goal in life? I remember sitting in the kitchen in my parents' house. I must have been 8 years old or something, thinking I want to be immortal. How am I going to be immortal? I got to do something in science. I want to become scientifically immortal. So this has been driving me my entire life, actually. It's not the applications. It's not the money. I will say another thing. When I was at Bell Labs, I had a full-time position at Bell Labs. First year, I was interacting only with my research colleagues at the labs. I found I was losing my motivation to do research. I started teaching part-time at NYU. I had one grad student at NYU, and ever since I've been teaching full-time in university with a part-time gig on the side in industry. To me, it's critical to interact with young people and to collaborate. It's a real motivator in terms of doing research somehow. So I love being a professor.
So let's follow. Yes, there is one question. Maybe I can give you mine.
Thank you very much. It was a beautiful talk, and how search trees are essentially at the heart of things. Maybe another avoidable question, unavoidable question is, in your opinion, so you also described how this has kind of paralleled the evolution of computing. And now, of course, we are at maybe the verge of quantum computing. So do you think that these data structures that we have today will still be the ones that we'll end up using, or do we need to think of different kinds of data structures to tackle quantum computing effectively?
I can give two answers to that question. Well, the first one is, all the algorithms I've been talking about are sequential algorithms with a one-level memory model, random access machine model. Things change when you allow multiple processors, and things change when you allow memory hierarchies. So there's been beautiful work in both of these areas, and personally I'm interested in concurrent algorithms, and in particular concurrent algorithms in a setting where there's no global clock. So you may have processes that start doing something and they die, and if you have multiple processes working on a data structure and something makes a change and puts it in an illegal state and then goes away, this is a problem. So even proving correctness in this setting is hard, let alone proving efficiency. So actually, on the disjoint set union problem, we managed to invent a version of that and prove a concurrent version, asynchronous concurrent version, and prove that it's efficient. It's one of the few examples of this. So I think concurrency is very important, and asynchronous concurrency we need to study more, and memory hierarchies are important. And quantum, I think all these data structures are not going to go away because quantum is very brittle in what it can do. It can do certain things really fast. There is the Shor factoring algorithm, which gives you exponential time speed up for factoring, which is going to kill RSA if the physicists ever manage to produce large-scale devices. And there's Grover's search algorithm and improvements thereof, which give you a square root speed up. But beyond that, I don't know. I think it's a challenge. I think quantum will do certain things extremely well if or when these devices are produced at very large scale. And these data structures are never going to go away even when that happens, because there will be a place for non-quantum computing forever, as far as I can tell. That is, PNNP quantum computing is not going to do it. That's my opinion.
Okay, I'll steal the last question for myself. So, you are the person who has seen punch cards as the very beginning of computing, and you see where we are today. We have many young people here who are doing their PhD or are right in a few years after their PhD. What would be your words of wisdom for them if they also want to be either immortal or have a slightly lesser impact on the world of research?
Read a lot. Read skeptically. Look at a paper, ask whether you really believe it or not. Reprove it for yourself. Ask what is missing. Be aggressive. Be aggressive in questioning speakers. Be aggressive in questioning your professors. One of the best experiences I had was so when I was at Caltech as an undergraduate, I took all the computer science courses, of which there were very few. They were all graduate courses. There was a course in automata theory taught by a wonderful Italian named Giorgio Ingargiola. And he prepared voluminous notes, and they were all full of mistakes. So some of us got together. We went through and figured out all the bugs in the notes and fixed them, and that was a tremendous learning experience. And actually, I would like to figure out how to make the learning experience more active somehow. Instead of giving lectures, have the students read the material and then come to class with problems and try to do problem solving in real time, something like that. You need to be active and be engaged with the material. The other thing I would say is don't follow the crowd. Follow your own passion. If everybody's working on it, you may be really smart, but you're probably not the smartest person. You need to find your own path. And I guess the last thing is you have to be willing to bang your head against the wall forever, go away from a problem, come back to it. This is hard. There's no getting around the fact that it's hard. But because it's hard, the rewards are incredible. That's my answer.
So I think this is a very good final words of wisdom to thank Professor Tarjan once more for his lecture on physics. And also, we thought a thing that you can remember us by. You probably go from university to university giving lectures, but how to remember us from. So I'll come back to what Dima just pointed out, that young people who study what you have researched in our lectures. And here is a small puzzle piece. It consists of 9 pieces. Professor Vilo himself designed this for us. It contains university buildings, but it is not as easy as you would expect. And it has been also a home task for our students to resolve it using algorithms. So thank you again very much, and I hope you enjoy your stay at Riga and travel at home back. Thank you.